My FIP topic is undersampling-based fast and low-power wideband spectrum sensing with block occupancy pattern. I'd like to start with the background first. Cisco forecasts that mobile traffic data will grow rapidly in the upcoming years. FCC also releases multiple bands for dynamic sharing in recent years. But before reusing the secondary devices or the spectrum service provider should detect the available spectrum. The challenge is that how to sense a wideband spectrum, like 1 GHz, to identify in-use spectrum in a fast and cost-effective manner. Researchers have proposed three kinds of solutions to the problem. The first one is using a wideband spectrum analyzer. However, this kind of approach have two drawbacks. First, the ADC of high sampling rate is power hungry. Second, the maximum sampling rate of a commercially available ADC is limited, which is 200 megasamples per second, which is not enough to cover a very wide band. The second approach is using commercial devices to sense the blocks or channels sequentially. This approach is very time-consuming and can miss short signals in some channels. The third approach, represented by compressive sensing and sparse FFT, choose to work on sparse cases so that they can find an approximation to the wideband signal. With undersampling, we propose an algorithm that can sense a dense spectrum based on undersampling. We start from the most easy case and named it noiseless uniform signal strength case. The spectrums are chopped into. We add the following assumptions to the spectrum. First, the spectrum is chopped into blocks, and the blocks are of equal lengths. The signal strengths of the frequencies in the same block are equal. Also, in baseband, the start points of blocks locate at a multiple of the block length. For example, if the block length is 8, 0 to 7 is the first block, 8 to 15 is the second block. We also set noiseless varying signal strength case to generalize our algorithm, where the signal strengths in the same block follow a consistent pattern and are not strictly equal to each other. To estimate the effect of noise, we add noises to both cases. Our contribution is that for given a spectrum of bandwidth n and block length L, we are able to sampling the signal with an ADC of sampling rate 2B samples per second and a filter of bandwidth B, where the requirement of B is that it is slightly larger than n divided by L. Our algorithm can ensure the low false positive and false negative, and the complexity is OB log B, which is also very low. So let's start with the uniform signal strength case. Usually, if we want to obtain the right frequency representation, we should avoid aliasing. But our algorithm chose the opposite way. Our main idea is to reconstruct the original frequency representation from its aliasing version. We represent the signal strength of the blocks as a vector x and its aliasing version y. In order to calculate the entries of x calculate a unique x from y, at least we need to make sure that every entry of x makes different contribution to the y vector. In this way, we get the requirement of b. The greatest common divisor of b and l is equals to 1, and the least common multiple of b and l is larger than n, so that we can have a system equation like ax equals to 1. However, if we directly calculate a to the power minus 1 times y to find x, we have two problems. First, we cannot make sure whether a is invertible. Second, the complexity of Gaussian elimination is the order of n cubed. However, fortunately, we find that we can append a and x, and by switching the sequence of x and the columns of a, we can obtain a circulant linear equation. And this provides us opportunities to ensure invertibility and reduce the complexity. Before I talk about the algorithm, C is the circulant matrix, and the first column of it cases, beginning with a series of ones and followed by a series of zeros. Before I introduce the algorithm, I would like to talk about varying signal strength case, because they use the same algorithm. In the varying signal strength case, we add a parameter to the one series before. For the one series, we can add a delta parameter behind. We have 1 plus delta 0, 1 plus delta 1, to 1 plus delta L minus 1. Because the C matrix gets more complex, the requirement of B is more restricted. B is a prime number here. And another problem is how we can get the value of the parameters. It is pretty straightforward that we can use a filter of bandwidth L to get a channel out of the spectrum and use it to calculate the pattern. And for the algorithms, our algorithm is mainly based on the property of a circulant matrix. A circulant matrix can be represented as the multiplication of a discrete Fourier transform matrix, a diagonal matrix of which the elements are its eigenvalues, and inverse discrete Fourier transform matrix. And because the eigenvalues of C can be calculated through DFT, and also we can use FFT to calculate DFT, so the entire complexity of the algorithm is dominated by the FFT complexity, which is OB log B. We add noise to both cases. Originally, we add noise to the original frequency representation, so that intuitively the equation will be C times the sum of x prime plus the noise omega equals to y. However, we take the noise out here, because first, the sum of independent Gaussian variables are independent to each other. Second, the parameters in C will affect the strength of noise. So we need to take it out. And we use the least square estimator to find the original signal, and we use the normal equation to ensure the invertibility. However, later we found that we can make sure that C to the power C is a invertible matrix. So we can simplify the noisy circulant solver to the one in the noiseless cases, and because of this, we will skip the part of noisy circulant solver. Another problem remains the pattern estimation in noisy varying signal strength case. We can still use an ADC sampling at 2 L samples per second and a filter of bandwidth L to get the channel pattern. However, we cannot get directly from one channel because there is noise there. But if we use this filter to and this sampling ADC undersampling the original signal, and all the channels will pair in the L bandwidth filter, each occupied a layer. And if we take the average of the noise, we will also take the average of noise, and the variance of means will be smaller than the original one. So the power of noise is also smaller. And we build a proof of concept experiment to evaluate our system. We use false positive and false negative to evaluate the system. As we can see from the graph, noise varying signal strength cases suffers less from noise than that of uniform signal strength cases, because the power of a channel in varying signal strength cases are mainly concentrated on the peaks, and those peaks suffers less from noise. But we can see also from the first graph that in low SNR cases, our algorithm works not that well. So we take a further step to improve the performance. We found two possible ways to reduce the impact of noise. As we can see before, the average of multiple estimations can reduce the power of noise. So, if we estimate the channel power for multiple times, we can also reduce the impact of noise. And there are two possible ways. One is we can use more devices. The other is that we can measure for a longer time. And this graph is what we can get if we use 5 devices. And the complexity of our algorithm is O B log B. But if we use the scanning approach, which we mentioned before, the complexity will be O L log B. And since that n is very large than L, so our algorithm and also n is very n is largely greater than n divided by L or B. So the complexity of our algorithm is smaller than the old one. And also we need only to sample once, but the original scanning method will need to sampling for n times. And further work include USRP implementation and find ways to further generalize our existing algorithm. Thank you.